Hello everyone, I'm going to go through the Year 12 revision vector skills questions. Alright, so I set a few questions in regards to vector problems that require vector addition, subtraction, as well as some basic and advanced trigonometry. Alright, so let's have a try at some of these. Okay, so question 1. An aircraft is traveling at 120 meters per second due north when it encounters a wind of velocity 30 meters per second west. Okay, so let's draw out those two vectors first. Alright. Alright, so we've got a vector which is due north. That's your 120. And you've got a much smaller vector going to the west. Okay, so I'm not attempting to do this to scale, but the proportions as close as I can do without actually measuring anything. Okay. Now, my resultant vector is going to go from the start of the first to the end of the second. Like so. Right, so 120, 30 meters per second west, and I need to know this, and I need to know that. Okay, so just using your basic right-angled trigonometry rules, we can work at x. So I'm just going to do this in one step, so just Pythagoras. X equals the square root of the sum of the squares these other two sides. Okay, and bring up my calculator. And 20 squared plus 30 squared and the square root of that. Okay. Okay, so in this question, well, I've got things to 2 significant figures. I think I should round this question to 3 significant figures. So 124, I think, is appropriate for this. Okay. And I also need to work out the direction. Alright, so you can do that with opposite and adjacent, so tan theta equals opposite over adjacent, thereby theta equals inverse tan of opposite over adjacent. Okay. Put that out. Alright. So about 14 degrees, but I've divided to 3 different figures, that will be 14.0. Alright, so full answer. The velocity vector, so I'll call that velocity vector, is approximately 124 meters per second in a direction of, I've got it here, north 14 degrees towards the west. Okay, there we go. Alright, so I think that one was pretty straightforward. Let's try the next one. The next one actually required a little bit more thought. It was a right-angled problem, but it was not another cookie-cutter example like question 1. Okay. Alright, so question 2. A boat has a maximum speed of 12 meters per second. The boat is attempting to travel directly across the river, which carries a current of 3 meters per second west. Now, the boat is trying to travel basically north, as I've drawn the diagram over here. Okay, so that's actually what the resultant vector would be. The vector sum of 2 other vectors needs to be directed north. So that's my resultant. Okay. Now, so I have a vector. So if the current's going to the west, so if we're going that way, basically you need to get a resultant vector like that, you have to point the boat in a direction that way. Now, I'm actually going to draw the second vector. Actually, in a way I could just draw it here, since I could draw it from the start. Okay, so I'll make the west one my first vector. Okay, so that's 3 meters per second. Yes. Right. And then my other vector, the direction I'm pointing the boat, is that way. Okay. Now, I don't know what direction that's in, but I do know that the boat can travel at 12 meters per second. That's actually, that's that magnitude. It's basically you're pointing the motorboard or the rudder in such a way that you face in that direction. Okay. So, to work out this, all right, so, all right, now basically this is, be careful with this, so that's those 2 squared equals 12 squared, all right, so rearranging that, velocity is approximately 11.62. I'm just going to write to that for now. I'll round off a little bit more in a minute. Right. I didn't pay a lot of attention to writing out significant figures in the values I gave you here, but it's about 2 significant figures. So we've got 3 and 2 and 2 over here. I'm just save that for the final answers, but I'll probably round to 3 in a minute. Okay, the direction. All right, so we're gonna have to measure the direction inside the triangle first, and then we have to think about how we're going to portray that. All right, so theta is equal to, now, if I go with my initial values, I've got the adjacent and I've got the hypotenuse. So that's cosine. So inverse cosine. Adjacent over hypotenuse. All right, about 75.5. All right, now there are a number of options you could write for this. You could say east 75.5 degrees towards the north. Now I think when I set this up in class, I might have suggested drawing it the other way, where I drew that vector meeting the end of there, and then drew the first vector coming up that way. But essentially it's the same, it's parallel. It's just I've drawn them in a different order. If you want to get the true bearing, basically you can just subtract that angle from 90, which I might just do now. Alright, so basically that angle measured from the true north, call that phi. Right, well phi would equal 24.5. So thereby you could say something along the lines of a velocity is approximately equal to 11.6 meters per second at an angle of 24.5 degrees true. All right. Now, as far as the answer, I would also accept, because of the way I've worded the question, in what direction should the boat's rudder direct the boat? So, yeah, direct the boat. So that should be in that direction, but Some people might have actually thought to point it in that direction. So if there's any answers that I'm not entirely sure what that would be, but if there's answers that are correct going in the opposite direction, I might accept that as the way the rudder points, because that's the direction it would point, away from the boat anyway. Okay, so that was part A. Part B. All right, just as when you work out that we've worked out the velocity component. Well, actually, we worked that out. We didn't actually need to work out the velocity component, but we do need it for part B, so I worked out part A. The part we actually needed was the direction. So what did true bearing? Yeah. Essentially, you could have worked just that out and satisfactorily answered part A, but I worked out the full velocity, which is going to be useful for part B because now I can work out how long it takes. Okay, so time. Alright, let's focus. Okay, time equals. Alright, distance on speed. Alright. So I'm dropping, because I'm working out a scale, I'm kind of dropping the vector notation. Alright, so the distance was 120 and we're dividing that by 11.6. Now I'm actually going to use the unrounded value for that. And what I'm going to do is I'm just going to delete this line. And then I basically can just do 120 divided by the previous answer. Okay. So then I don't get the rounding error, and I can just round this to through some figures. 10.3 seconds. There we go. Okay, so that's question 2. All right, moving on. Question 3. Okay, so this is a classic two-dimensional question that results in an isosceles triangle with a vector diagram. So a classic problem people have with these sort of questions is they'll kind of draw out the situation as it looks. Another one is when you have in momentum you draw vectors in towards the collision. Now you've got to think about the mathematics. Follow the procedure for your vector addition. In this case, actually, there's a subtraction. Okay, so question 3. A ball traveling at 6 meters per second collides with the wall. A bit of that's cut off. Pardon me. No, didn't want that. Trying to get the perfect zoom. No, that'll do. I'll just bring it across. That's the problem with the words were getting cut off. There we go. A ball traveling at 6 meters per second collides with the wall at 40 degrees to the wall, as shown. It rebounds with the same speed and angle. Find the change in velocity. Now, I've also included the change in velocity. By definition, is the vector subtraction of the final velocity take the initial velocity. Now that's a vector subtraction. Okay, so just a little hint about vectors subtraction. Do not just subtract them as if they were scalars. So yeah, if you just subtract 6 meters per second with 6 meters per second as scalars, you get 0. But that's not vector subtraction. That's a scalar subtraction. Okay, turning around. All right. So the way we do vector subtraction, as a reminder, is you actually you do a vector addition of the first vector and the negative of the one you were actually subtracting, which means you reverse the direction of the second vector. So let's do that. Let's draw that over here. All right, so seeing over here, where my mouse is, we've got, that's your final and that's your initial. So initial would be actually pointing this way. So I'm actually going to draw something that goes down that way and then up that way. Okay, so the vector sum, careful. All right, so I'm going to draw that. All right, and I'm going to draw that. These two should be the same length, but not quite. and that's actually measured off the wall. I didn't actually. Notice I'm not actually measuring any angles. I'm just drawing non-scale diagrams. It's approximations to the scale diagrams. So I'm using trigonometry. Okay, so that's 40 degrees, which is not. It's actually, I've drawn it a fair bit larger than that. That's all right. And then that one is the reverse. Okay, that's 40 degrees actually around from that median line. Okay, that's actually, I've drawn in vertical lines. I've drawn a bit more solid. So that's what I'm measuring off. And these are parallel, so you can use that. Okay, the resultant vector. Okay, start with the first and the second. All right. Now, so that was V, and that is V naught vector. Okay. Sorry, I'm having trouble with. There we go. Okay, let's focus. All right. So what we have here is an isosceles triangle. So 6 meters per second, 6 meters per second. All right. Alright, so that's... Now basically what happens is you draw a line down the center, and for those who've done these problems before, this ends up being at right angles to the wall. You don't have to do like prove it using geometric rules. If you can kind of see it, you can just go with it. But if you want to prove it for yourself, you can certainly do so. Basically, the idea is like using parallelism rules. You can just move that 40 to there, and then once you've shown that that's okay, so with parallelism rules, that's 40 as well. So thereby, okay, that bisects the apex angle. That makes that right angles to that, and thereby that's right angles. The green vector is at right angles to the wall that it came out of in the first place. Okay. So when it comes to direction, we can say normally or at right angles to the wall, normally out of the wall. Okay, so remembering the way you can solve these sort of problems. Okay, I'm going to call this whole vector delta V. Okay, then the way we solve these problems is we just bisect the isosceles triangle. Make two right angle triangles. So that now is half delta V. You've got 40 degrees, and you've got 6 meters per second. All right. Now, the way I've written it here, I think that just cuts down the amount of work. Some people were writing, they were just calling, they bisected the base and called that x and x and solved x, and then remembered to double it afterwards. That's fine too. As long as you're doing a method that is right. It's all kind of the same thing in the end. But this is just going to be done with one equation. All right, which is, okay, we've got opposite and hypotenuse, so it's sine. So sine 40 equals opposite over hypotenuse. All right, so multiply the 6 across and times both sides by 2. Delta V equals 12 sine 40. Work that out. Oops. Okay, 7.71. So I'm going to say delta V vector is approximately 7.71 meters per second normally to the wall. Sorry, I'm going to rephrase that. Normally out of the wall, make it more particular. Okay. Sorry. Normally out of the wall. All right. I'm going to need a new page. that's question 3. So that's all I got you to do for that. There was no full-on questions for that one. Oh no, sorry, there was. Okay. Tell a lie. Okay, well that one's easy. So, let's focus that. Okay. Last thing. I have a follow-on question. I asked you to work out acceleration. Acceleration is delta V on delta T, which is, we'll go over 7.71. Divided by, okay, it happens over 0.04 seconds. Alright. Also divided by 0.04. Okay, so it rounds to about 193 meters per second squared at a direction out of the wall. Alright. Okay, so the next one is another vector addition. So it's a pretty simple one. So we have 2 tugboats pulling at angles 30 degrees to from the direction of motion. Alright, so vector sum of that. The first vector at, I'll make it a bit bigger than that, 30 degrees from this, and then do another one, 30 degrees down that way. Okay, now I'll put a 30 in there, and okay, 30, 30. 120. Well, then we've got our measurements of 1.2 times 10 to the 5 newtons, and it's another isosceles essentially. Okay, and the resultant vector going across to the right. Or, as in the question, I actually called it horizontal. So just, and the final answer is horizontal. And again, you can prove it as well. You can prove that, well, that's horizontal, that's parallel. You can demonstrate that. Well, I already kind of have here with that and that. Yeah. Okay, horizontal. So, all right, let's get this one done. Just for sake, but I'm going to do something different. As I mentioned in the when I gave this out, that you should pick the simplest method, so you can't just cut it in half and make it a turn it into a 2 right angle triangles and just solve one. But I'm just going to do it with the cosine rule this time. Okay, so x squared equals a squared plus b squared minus 2ab and the cosine of the angle opposite the measurement you want to find. So actually that's getting cut off. Alright. That's not good. That's cosine 120. Alright. Alright, well that equals, let's just do that. 1.2e5 squared plus 1.2e5 squared minus now basically that ends up being 1.2e5 squared again, because it's minus 2 times 1.2e5 squared times cosine 120. equals 4.32 times 10 to the 10. Okay, x is equal to the square root of that. So I'll find that out. Last answer, power of a half. I find that easier to do than just shift square root, then put in shift answer. So last answer, power of 0.5 is the square root. Alright, so it's about, putting that scientific notation, 3 sig figs, 2.08, 2.1 times 10 to the, oh, it should be the same magnitude, shouldn't it? 10 to the 5, double check. Okay. Yep, 3, 4, 5, correct. Okay, newtons. And then your force, net force, .08 times 10 to the 5 newtons in a direction of horizontal to the right. Okay, so that's that. Now, question 5 isn't one you would ever get set into physics. You've done these kind of sort of questions before, these in maths, but yeah, I would not send you a question like this in physics. But this is just a question where we're just going to throw. I'm just throwing a some numbers at you and see if you can handle scaling triangles in this context. All right, so this is where you will need your sine and cosine rules. So a cycle travels 7 kilometers in direction of west, 32 degrees towards the south. So draw west and switch 30 degrees or so to the south. All right. All right. Let's do 7. That's my west. I'll call that 30 degrees. All right. I'll leave putting a number on there for now. Then we go east 5 degrees towards the north. So so it's mostly east and a slight angle towards the north, something like that. Okay. And that one's 10. East over here, that's 5 degrees. All right, find the total displacement. Okay, so gone that way, and we'll go that way, and now we go this way. All right, you might want to draw a diagram larger than that for this sort of question. I would recommend that. Okay, so 7 and this is 10 kilometers. All right, now we need to get some angles inside that. So if we think about this, if I extend this east-west line on the, I'm thinking about which one's better to do. Probably the one on the bottom. Extend that forward. Okay. So those are parallel. So it's 150. Yeah. They have to add up to 180. Okay. So we're closing in. So we've got 5 degrees here. Then basically, if that's 150. And that's 5, then that has to make up the remaining value to make 180, that part inside the triangle. So we'll get a first one inside the triangle. Okay, so that's 155. From 180 is 25. Okay, yeah, 25 plus 5 is 30, plus 150 is 180. Okay, good, we've got 1. And that's enough to get the other side. So you notice that works out nicely because that's the angle that's opposite this, the red vector. Okay, so we actually can use the cosine rule to find that, so I'll just call that, that's going to be my x. And I'm just going to go straight into the cosine rule, and I'm even going to take the square root. Okay, alright, so 7 squared plus 10 squared minus 2 times 7 times 10 times cosine 25. Okay, let's see that, how that goes. About 4.7 kilometers. Oops. Yeah, that's out of sight. There we go. That's better. Alright. So that's your distance, though, from where you started. Displacement, remember, requires direction. Okay, so what we could do is, if we can get this angle, that would be helpful. That angle there, we'll call that phi. Okay, then that is opposite the length of 10, and we're going to have to use what we just found here. So we're going to use a sine rule for this. So, all right, we're solving sine phi over 10 equals sine 25 over x. And basically I'll just write it out like this. Okay, I can times the 10 across. And then the inverse sine of that. Okay. I prefer guys to do calculations in, rearrange and do these, but there's a time and place to simplify and work out some values, particularly in questions where you get zeros and ones and things like that. Okay, but let's have a go at this. Okay, inverse sine bracket fraction 10 sine 25 over my last answer. Okay, so that angle is, now look, I've just got it 64.0. Alright. Alright, so that's the one up here. Now we've got 30 degrees here. So that's essentially, okay, like we could have a south line here. Hang on. That's 30 degrees. That should only be 4 degrees past here. It's not a scale diagram. Because 30 plus 60 is 90, so that should take you around to the south, and you've got 4 degrees left over. So essentially that's equivalent, the direction of this is south 4 degrees to the east. Or essentially, well, what I've just worked out here is that full angle around from there is 94. So that's west 94 degrees past the south. That's not a conventional way of writing a compass bearing. So then it's west, south 4 degrees towards the east, or if you're 4 degrees towards the east, you're essentially true bearing. Okay. So that's 4 degrees there. Then your true bearing should be towards from north to south is 180. So then that is 176. I know it doesn't look like it on the diagram, but I also did something wrong in the calculations. That's what it is. It's just I haven't got my angles worked out. I did the lengths correct, but the angles were not. So that's going to change things around. Okay, so final answer. Displacement. Enough. Is approximately 4.7 kilometers, an angle of 176 true. Okay, and that's question 5. Alright, so hopefully you guys were able to correct your mistakes. If anything you still don't get, let me know. And again, some parts of this was just a test of your ability, and this is all things you should be able to do, but will not necessarily be tested on in physics. Alright, see you later.